Hi, everybody, and thanks for coming to the workshop. It seems like we're going to have a super exciting program. So I'm really happy to also have an opportunity to share with you some of our recent work in this space. So as you all know, constraint solving and optimization is used through many sectors of the economy for all sorts of problems. But the size and the complexity of the problems that we are trying to solve keeps on increasing. And so, working on the technology behind solving this problem is a very important endeavor. And importantly, as the kinds of problems we are trying to solve keep on changing, it's important to have techniques that can support that evolution in the algorithmic techniques as quickly as the problems themselves evolve. And so that's where this idea of leveraging machine learning within algorithmic design for combinatorial hard problem comes in, and this domain has really started growing at an increasing speed over the last few years. Like as recent as maybe like 2016, 2017, there was hardly any work in this space, and now we see a growing and vibrant community with new results. So in my own work, I guess I focus on two directions of integrating machine learning and combinatorial solving. The first one on which I'm going to focus today is infusing discrete optimization with machine learning, where we are trying to augment discrete optimization algorithms with learning components so that we can make them more easily adjustable to new problem domains. In the second direction, we're thinking about how we can infuse machine learning with constrained decision models. Often machine learning models are fitted and trained in the context of being useful for some downstream combinatorial tasks. So here, learning methods need to incorporate the combinatorial decisions that they inform downstream. So you can see how these two are kind of two ends of the same symbiotic relationship. So within the infusing discrete optimization with machine learning, one can think about many ways in which to incorporate machine learning. And in particular, one of the things that we've strongly focused on is thinking about algorithmic frameworks and how some of the heuristic components within this established algorithmic frameworks can be made ML-guided. For example, guiding a greedy algorithm for graph optimization, or guiding different components within the branch and bound search for solving mixed integer programs, including branching, heuristic selection, and backdoors, which I'm going to talk about today, or even guiding meta-algorithms for mixed integer programming like large neighborhood search. And more recently, also in the context of another combinatorial domain, multi-agent pathfinding, where similarly state-of-the-art methods use research-based algorithms, and we have developed ML-guided versions of a lot of the algorithmic techniques there, from conflict selection, which is kind of the equivalent of branching in MIP, to node selection, to large neighborhood search for the multi-agent pathfinding. In the opposite direction, in infusing machine learning with combinatorial optimization, here the idea is that we want to train machine learning models to predict parameters for our decision-making downstream, taking into account how they're going to influence the decisions that we make. In a sense, what we want to achieve is the best end-to-end quality of the pipeline of predictions and decision-making, plus the realization in the real world of those decisions under the true parameters of the problem. So we propose this decision-focused learning framework, which kind of formulates that thinking in the context of combinatorial problems, and showed some results of how to do this for submodular optimization linear programming. Then we extended this to differentiable k-means, so clustering, which is used as a surrogate for graph optimization problems, and then to the general notion of integrating mixed integer programming as a layer in neural networks. And we've applied this in a couple of real-world domains, including informing tuberculosis health visits in allocation in India, as well as wild trafficking route prediction So this is a very, again, a big domain of work that this is just my group's work, but there's many more related works, and we're going to hear, I think, several talks in this week that contribute to this direction as well. And our most recent work with our collaborators at MetAI, which uses differentiable optimization for improving solvers for mixed integer nonlinear programming. So I'm going to talk today about two particular subsets, in particular here. But if you want to hear more about some of this stuff, there is two posters from my PhD students. Aaron has a poster that presents MIPAL and CIRCO, and Tawan will present a poster that shows our work on multi-agent pathfinding. So please go and find them this afternoon and ask them questions, hard questions. Okay, so today, I guess I'm going to focus on the direction of integrating machine learning into combinatorial optimization, where we're trying to leverage learning to automatically customize combinatorial algorithms for problem distributions. And so we're going to focus specifically to mixed integer linear programming, and I'm going to show you two examples. The first one is learning backdoors for MIP solving, and the second one, fresh off the press, is learning large neighborhood search strategies for large MIPs. Both of these examples are kind of in contrast to some of our earlier work, which basically designed machine learning guided components inside the branch and bound. So for example, guiding the selection of branching variables or guiding the selection of primal heuristics, which in both cases requires open box, white box access to the solver. Right, and that has created quite a bit of turmoil and difficulty, right? So depending on what the API of different solvers is and how much access they give you to actually reinventing the guts of the solver, right? So the nice thing about both of these works is that they actually need access to the MIP solver only as a black box. So they're kind of on top of MIP solver, so they can be implemented in the context of any of the existing or future mixed integer programming solvers. Okay, so as you all know, mixed integer programs are a very flexible mathematical program framework where we have a linear objective, linear constraints, and discrete and continuous variables with a lot of real-world application domains in business, society, economy, sustainability, etc. Right? In particular, in my work, I use MIP for conservation planning and disaster mitigation planning. But obviously, there's many, many more important applications, and therefore, again, improving our ability to solve this diverse set of problems in different contexts under different distributions is really important. So as I mentioned, there's a growing community working on machine learning for combinatorial optimization, in particular for ML for MIP solving. There's a whole bunch of papers related to selecting variables, selecting nodes, selecting primal heuristic, selecting cutting planes, and I'm sure this list is already outdated. So I'm sorry if anybody's favorite paper is not here. I was just chatting, I think, with, in the break. The nice thing is our community is growing. The bad thing is hard to keep track of who is doing what. So if you have something that's missing here, come and let me know and I'll add it. There's obviously been a long community of using ML for hyperparameter tuning for solvers, as well as machine learning in other combinatorial optimization problems like routing problems, satisfiability, and graph optimization. Okay. So starting with the first work that I want to share with you today, learning pseudo-backdoors for mixed integer programs. This is joint work with my student Aaron Ferber, as well as Jalin Song and Yi-Sung Kyu at Caltech. So as I mentioned earlier, branch and bound research is the main way that we solve mixed integer programs. And it's been shown that one of the key components of the running time of these solvers is how do we select the branching variables, okay? And so informing branching variable selection can actually help us speed up this tremendously. So we're going to focus on this, but instead of changing the inside strategy, we're going to do something different. In particular, we're going to use the notion of backdoors. So the idea behind backdoors is that backdoors is a set of key variables in our problem that kind of captures the difficulty of the combinatorics of the problem. So if we're able to figure out which these key variables are and we search over possible assignments to them, the rest of the problem kind of falls apart through constraint propagation, and the assignments of the remaining variables are obvious through propagators. Okay, and so the idea of backdoors was actually first introduced in 2003 in the context of satisfiability, explaining the very high variability of such solvers on real-world instances, where with randomized branching, you would sometimes get extremely lucky and get a very short run, and other times a very long one. Later in 2009, during my PhD, I generalized this notion of backdoors to mixed integer programs, and thinking similarly, what are the set of key variables in the context of optimization. And in particular, the definition of a strong backdoor for MIP is that it's a subset of the decision variables such that branching only on the subset yields an optimum solution for the MIP problem, right? So that would mean that every time we are out of these variables in the backdoor in our branch and bound tree, we essentially can prune the node, right? Either because of infeasibility or because of bound. So clearly, this is kind of a more messy and more complex notion than for satisfiability, where we have to only worry about feasible or infeasible. But we actually, in this early paper, showed that indeed some instances in MIP-lib contain extremely small strong backdoors for MIPS. And then the idea is, again, like in SAT, the holy grail, the promised land is that if they truly exist for real-world problems and we are able to find them, then suddenly our solvers will be able to run much faster. Okay, but obviously, finding backdoors is actually an even harder problem than solving the original combinatorial problem. So we're going to have a hard time, and sometimes when we guess, we're going to be wrong, right? So what happens when we only allow branching on a set of variables, but these variables is not a true backdoor, so some of the nodes at the bottom of that partial search tree are still open, then we don't really get a proof of optimality. So for this work, we kind of soften the notion of backdoors to what we call pseudo-backdoors. And so basically what we're going to say is we're going to guess this backdoor set, give it to the solver, and tell it to branch on this subset of presumed strong backdoors. But if it gets to a node where it has branched on all of the variables in the strong backdoors and still not finished, it's allowed to now continue to the rest, right? So it's kind of this soft definition, which allows us to still preserve the optimality and completeness of branch and bound. Okay? So, but the idea is if we have guessed correctly, we're still going to have faster solve time and more efficient gap convergence and hopefully higher quality solutions within given cutoffs. Okay? So as I said, yep.
So once you have solved the problem, I wouldn't say easy, I don't think so, but it's possible to go back and check if there was a backdoor.
Yes, except like generally, if you're not actually looking for a small set, almost even small trees will contain almost all the variables. If you're somehow not gearing your solver to try to minimize the variables. Yeah, so you could always ask basically your tree, like which variables did you branch on anywhere in the tree, right? You can, if you have white box access, you can augment your solver. Anytime you branch on a variable, you set the flag to 1. So if you've branched ever on it throughout the whole branch and bound, it will be set to 1. At the end, you can just read it out. But my guess is that you do that, and if you just are running regular branch and bound search, almost all the variables would be branched on. Because even if it's kind of like symmetric, since it's not trying to get to a small set, it will just choose arbitrarily. Okay, and so as I said, there's been a growing work on backdoors in the SAT community as well as in the MIP community. Following up the initial work on MIP backdoors, which used a very, very simple heuristic to basically sample potential backdoors based on the root LP fractionality of the variables, basically saying variables that are more fractional in the root LP are more likely to be part of a backdoor, and sampling multiple times and checking. Then there's been a follow-up work by Fischetti et al., which formulates the backdoor selection with a coverage problem. Dvorak et al. In 2017 proposed using global couple variables to try to fracture the MIP. And most recently, Elias Pashtan and myself were looking at finding backdoors using Monte Carlo tree search. But the key idea here is that there is evidence that real-world problems have this core set of variables, and hopefully by improving our ability to solve them, we can also try to design faster solvers. Okay, so in this most recent work, basically that uses Monte Carlo tree search to search for backdoors, what we did is we tried to find small backdoors as possible for individual MIP instances. So this was more like an approach to find backdoors, not to learn them, right? So here we were looking at Monte Carlo tree search with reward that corresponds to the tree weight, and showed that we are able to find better backdoors than the LP fractionality procedure that I had proposed earlier. So this kind of gives us hope that maybe we can, through this expensive procedure, can actually get a good labeled data set for backdoors in the future. Okay. So, but here what we're going to do is we're going to try to learn to predict these pseudo-backdoors for, again, over a distribution of instances, not in general. So as all the problems based on the ML-guided combinatorial solvings is we're trying to create a framework that allows us to fit the parameters of the ML model within a particular distribution of MIP instances.
So, could you perhaps explain what's so a more formal definition of what a good backdoor is? How do you know if something is a good backdoor or not?
Okay, so a good backdoor, I guess I had it a little bit earlier, but a good backdoor is a backdoor that branching on these variables results in a fast running time or finding solutions early, better solutions within the same time, right? And the ideal backdoor, if you find a true strong backdoor, basically you would only need to branch on those variables. So therefore, yes. But in our case, because we are not going to, in many cases, we are not going to be able to find strict, strong backdoors. What we're going to measure is the runtime that it takes, or the quality that we get within a certain time cutoff. Yes.
So would the backdoor be for finding, let's say, the optimal solution, or would it be the same backdoor for proving optimality?
So they could be slightly different. Yes. Here we are because we are doing the black box access to, we are basically doing the two together. So we are not assuming that we have the solution yet. Any other questions before I move on? Okay. So how are we going to try to select these backdoor sets? So set prediction is hard. If you worked on any problems that require set predictions, is like not trivial to be thinking about that process. And so we kind of struggled a bit of how to define this learning task. And so what we landed on is basically sampling backdoors and scoring them, basically building an ML component that will predict how good a potential candidate set is, as opposed to actually constructing the sets themselves. So basically for every candidate backdoor set, which is a subset of variables of particular given size, we're going to associate a value, and this value, when the learning is done, should be correlated to the running time that we get when we give this backdoor as a priority branching to our solver. Okay, so the idea is if we sample a whole bunch and we have a good model, we're going to be able to select the best out of those and use that with our solver. However, we have to add a second component, which is this classifier, whether it basically lets us decide whether to use the backdoor at all or we just go with vanilla Gurobi. And why we needed that is because maybe none of the candidates is good. it might still predict very well which is the best out of them, but the best is still a bad one, right? So at some point, you need to have like a fallback way of escaping, committing to something that's not going to be useful.
So sorry, I didn't really get how you sample the backdoor sets.
Yeah, I'll get there in a second.
Okay.
So this classifier will let us basically save ourselves when there's really nothing good. Okay, so this is kind of the overall architecture, right? So what we're going to do is going to use the original method for sampling backdoors based on the LP relaxation of the MIP at the root node, and basically sample a whole bunch of backdoors sort of a given size. That's to answer your question, right? So where the probability of selecting a variable in the sample is proportional to how fractional it is in the root LP. The more fractional it is, the higher probability of sampling it. Okay? And so then we're going to feed this collection of k backdoors into the scoring module. It will predict a score for each one, and then one gets selected. We'll feed that into another model that will tell us whether to use it or not at all. And if we do decide to use it, we give the priorities to the Gurobi solver. Otherwise, we just use vanilla solver. Okay? So what we're going to do for our scorer model is use kind of now standard representation of MIPS for learning, where we have the bipartite graph between variables and constraints with the corresponding features as used in Gassa et al. And in particular, we're going to just add one extra variable feature, which will say 0 or 1 based on whether it's in the proposed pseudo-backdoor or not. Okay? And then we're going to use a graph neural network with attention pooling to predict the value for this backdoor. Okay? So this architecture is kind of very similar to what we've seen before, except that we end up with a single value at the end for the backdoor set. So it's a single value that says how good is this set. So here, we're going to have, after like the 2 passes of message passing in the GCN, we're still going to have embeddings for all the variables. Then we have some last layers that combine all of that into a single value. And our loss is based on this overall score that's associated with this set as a whole. Other questions? And so we're obviously going to do this for multiple backdoors. Okay? And in the classifier, we are basically going to use the exact same architecture, except now we're going to be predicting 0, 1, whether to use it or not. And so our loss here will be different. Okay? So as I mentioned earlier, our features are essentially the same as in the Gassa et al. Paper. I don't know why this is missing. So I'm going to go quickly through that because I assume most of the people in the audience are familiar with this.
If a variable is integer in the LP, does it have 0 or does it have like an epsilon chance of being selected to be part of a backdoor?
Epsilon.
Okay.
Yeah.
And do you only, so solution fractionality is the sole choice of sampling for the backdoor. None of the features here, these are just used for the GCN.
Yes.
Yeah.
Although the LP functionality is one of the standard features, but yeah. But in a sense, this is independent. We can change this architecture any way we like, and we can actually change our sampling procedure as well, right? The LP rounding-based procedure is just some component that lets us sample candidates. Okay, and as I mentioned, we're going to do two rounds of message passing within the GCN, and then use attention pooling to aggregate the final representation in the MIP graph into a single scalar value. Okay, and so here for the scorer, what we're going to do, the loss we're going to use is a ranking loss. Okay, I have this a little later, but the idea is that what we're learning is to predict what is the best backdoor out of the candidates we have during training. Okay, so training data collection per problem class. It's always on a distribution of MIP instances. I mean, obviously, I Aaron can remind me if we tried it on MIP. Did we try at any point to try to just combine mix and match? No, but you can always try it, and people with the branching, some of the ML guided branching, generally I find that the whole idea for me, the idea about ML guided components in combinatorial algorithms is really exploiting the fact that we can have something that can specialize to exploit the structure within a problem domain. That's why we don't have a heuristic that can solve or work well for all NP-hard problems, right? And so, but ML-guided models allow us to basically have a procedure that applies to all of them. You just need to fine-tune it to each one. Okay, so to collect the data for training this scorer, what we do is we spend a lot of compute time to sample backdoors, solve the MIP, and record the runtime for all these candidates, right? And additionally, also record the Gurobi runtime without backdoor, so that we're going to need for the classifier to decide basically whether running Gurobi without a backdoor would have been better. Yes.
Did you say how you do the sampling? So from what distribution do you do the sampling?
The backdoors?
Yeah.
So based on the root LP, the relaxation of the MIP, you look at how fractional which variable is in the root LP, and basically that gives you a probability. The more fractional it is, the higher probability of selecting that variable during the sampling.
Right, and you want to make sure that you have like a balanced sample? Do you have a balanced sample of positive and negative
No.
instances? You do not?
No,
So
not
how
sure.
do you pick your negative instances?
So there's no negative instances, so we sample a bunch of backdoors, we evaluate each one of them, so we know the runtime, and during training, we're going to have a ranking loss. We want our scorer to predict higher value for ones that have better runtime. But as we'll see in the next one, actually exploring something like contrastive loss for here with positive and negative examples could also be a good way of extending and improving this work.
I was confused because you said that you have this set of nodes and you wanted to see if those are good backdoors or not. And so I thought it was a binary set of instances, right? I have a set of nodes, 1, 0, 1, 0, right?
Yeah, so yes, so a candidate set, a candidate backdoor essentially is a vector of zeros and ones, where the 1 says this variable is part of the backdoor, 0 is not part of the backdoor. And now this vector, which is this candidate backdoor candidate set, is going to say that during branching, I'm going to prioritize branching only on the ones that are set to 1, right? And so the idea is that this vector, this backdoor set, will be good if, when given that priority to the solver, the runtime is small. So what we want... Yes, exactly. So these are all I don't want to go back too much, but these are all vectors, and each one of them has a value, which is the runtime that each one of those candidates resulted in, and now our ML model is also going to predict a value associated with it. We want the ranking across this predicted value to match the real runtime ranking. Okay. So, I lost my, so as I had mentioned a few times, the trained value estimator is going to be trained with a ranking loss. And so at the end, we're going to be predicting these values for each candidate set. So then the classifier is going to have the similar, actually identical architecture, same features, also 0-1 feature, extra 0-1 feature that basically says is the variable selected in that best backdoor that the scorer gave us or not. But now the prediction is a 0-1 label that says use the backdoor or don't use the backdoor, and the label comes from us comparing from our collected data whether the Gurobi runtime without any intervention was faster or slower than the runtime that we got with this particular backdoor in our training data set, okay? And so, so we are basically using the same data, the same architecture, but training a classifier. Okay, so let's see how this works. We evaluated in 3 domains: neural network verification, where we basically want to find whether we can have a minimal perturbation to an input to a neural network to basically fool it, to make it misclassify something. So there is a MIP model that can actually solve this, that finds the minimum, decides whether there is a perturbation or a minimum perturbation that can achieve this. And this was a benchmark that was proposed in an earlier paper by Vinod Nair, where they were looking at machine-guided a large neighborhood search, I believe. So our second domain is going to be facility location, where we are trying to figure out, given startup and transportation costs, which facilities to open in order to minimize the total costs, both of the open facilities as well as the travel cost of the customers to the facilities we choose. And again, we're going to have here two hardness settings, easy and hard, and the instances are randomly generated. And finally, our hardest benchmark is the generalized independent set problem, which now has been used as a benchmark in several papers, where we are given a graph, edge removal costs, and node values. And what we want to do is we want to pick a set of nodes to include. So basically get an independent set, but we're also allowed to remove some violating edges by paying the cost for them, and we want to maximize the profit. So here again, we have an easy and hard setting. And so this problem is actually originally comes from forestry management, but also has other applications. So we have 100 train, 100 validation, 100 test instances for all of these benchmarks. So here are the results. So what we get is that we are comparing in actual wall clock time, in terms of runtime, Gurobi with our model, which is the scorer plus the classifier. And we can see that we have improvements on almost every single benchmark except for the facility easy. Also, just as an ablation, we provide in the middle of the result for just the scorer to show that there is a benefit to basically having that extra step of classifying at the end whether we want to use the backdoor at all or not, because in some instances, often the samples we get are not good enough. So we are able to show that we can use ML-guided backdoors to actually speed up wall clock time for these problem distributions. And so if you look at more closely to the empirical results in terms of win-loss and tie results, which this is basically looking at how many of the 100 test instances does our approach have faster runtime or slower runtime than Gurobi. We can see that we basically get quite a few wins and ties using our method as compared to Gurobi. Almost all of the instances are improved, right? So it's not only on average, but also in individual instances.
Do you have any statistics about how often it's decided to not use the backdoor?
So you can basically get a sense of that by looking at the scorer, because the scorer, the one in the middle, basically has no option but to take the backdoor. So any difference between the second and the third line in each one of those will tell you how often, in essentially, this classifier intervened, right? So, so here, for example, let's use the top one. The top one as an example. We had 31 losses to Gurobi. And this one basically has like 18 ties, which means likely several of those losses where the backdoor was not a good idea. Now the classifier told us just not to use it. So a tie is essentially that the tie tells you most likely what we did is we just ran Gurobi. Because it's really hard to have the exact same runtime unless you're literally just running Gurobi, right? So all the times are the ones where you're choosing not to use it. Thanks for the question. That's actually a good way of talking through it, that really the ties are the times where we are saying, okay, we didn't find anything good. And so I really see this as a proof of concept. Ideally, I would like us to find, to continue working on improving these prediction models. Obviously, our data is sampled with not a very good oracle, right? It's based on this bias sampling from the root LP. If we can use something like the Monte Carlo tree search method to get better backdoors, or there is recent work by Shantan Uday at Georgia Tech where they have a way of actually finding optimum search trees for some classes of problems. So from there, actually having really like maybe a way to find some optimum backdoors. But both in terms of the data collection as well as the actual learning architecture can be improved. But this is a very good already proof of concept that in fact we can use this high level guidance based on the idea of backdoors to improve wall clock time for solvers like Gurobi, which are already highly optimized. So I guess I already said my key takeaways. Any last questions before I move on to my second thing? Oh, I don't know how much time. I didn't start my clock, so I have no idea. How am I doing on time? Is anybody?
Yeah, you have a question, so you have like maybe 20.
Okay, if I have 20 minutes, then I'm gonna skip questions for now, since we've had questions throughout the talk, and really want to show you the next part, which is, again, a black box access to MIP, but thinking about how to improve a meta algorithmic framework, the large neighborhood search, a very widely used algorithmic framework for really, really hard combinatorial problems in the context of MIP by using contrastive learning. So this is joint work between my students, Tawan and Aaron, together with our collaborators at Meta AI, Yundong Tian, who is here, and Benoit Steiner. In fact, a big chunk of this work was done while Tawan and Aaron were at internships with Yundong. Okay, so large neighborhood search, was the idea behind large neighborhood search is that what we're going to do is we are going to find an initial solution to our problem. So first of all, this works for problems where finding feasible solutions is easy. So not like problems like GISP where finding feasible solutions is really hard. But there's plenty of very hard real-world problems where finding feasible solutions is easy, but finding good solutions is hard, right? So that's where large neighborhood search applies. Then once you have this initial feasible solution, you start try to improve it by basically destroying part of the solution. So you choose a set of decision variables to unassign. You keep everything else frozen, and then you repair or reassign those variables that you've chosen to destroy, right? So in a sense, you keep a big portion of the problem where it is, then you have a smaller problem of the same type, optimizing the same constraints, but over only this subset of k variables that you have destroyed, right? So in the destroy step, we pick which variables to unassign, and in the repair step, we use some methods to reassign them, okay? And so in the context of MIP, the repair step will be basically done by a MIP solver, which solves the sub-problem over the variables that you have unassigned, okay? So LNS has been highly successful meta algorithm, especially for very large-scale real-world problems. So it's been applied not only for MIP, it's actually a lot of its early successes are in constrained programming. It's also been used extensively for routing problems, like vehicle routing, TSPs, also for scheduling. Most recently, it has been successfully used for path planning problems, where Tawan's work was, which basically introduced ML-guided version of LNS for the path finding problem. And then the LNS for mixed integer problems. So a lot of the early work on LNS for MIPS was really in the context of a primal heuristic within the branch and bound, right? But actually a lot of these same ideas that were developed in the context of branch and bound perfectly apply to also LNS as a standalone method. So all of these citations, I guess, are nothing to do with learning. They're just LNS methods for different combinatorial optimization problems, okay? But as with all the algorithmic framework, what are we looking out for is opportunities where we can replace some heuristic components that are key to the success of the problem with an ML-guided version. And in this work, what we're going to be looking at is at the destroy method and how we can replace it with ML-guided heuristic as opposed to some handcrafted way. So for a lot of the non-MIP-based work for LNS, usually there's some kind of a custom heuristic based on exploiting the structure of the problem to decide which variables to destroy, looking at the graph of the problem, looking at the schedule, et cetera, et cetera. Okay, so this actually started with inspired by an early work that I did with my collaborators at Caltech on using imitation learning for large neighborhood search for MIP, where it was basically the first work on using ML for LNS to solve ILPs. But there, I guess the version of LNS we decided to focus was this decomposition-based LNS, where we, instead of learning how to select one set, what we did is we said we're going to partition the variables into k subsets of equal size, and then in turn, round robin, re-optimize, repair each one. So then we were basically learning how to predict this partitioning of the variables into these k equally sized problems, okay? So we were looking to predict good decompositions from offline data, where we sampled a lot of possible partitions, and then we used imitation learning, both based on behavioral cloning and forward training, in order to do our learning. So in that early work, we showed some good success. In particular, we showed that we were able to learn better strategies than random. And then we also showed that we were able to improve the quality of the solutions found by the learning guided methods based on our imitation learning here, right? Behavior cloning and forward training. And we compared to also an RL version of that. However, overall, the improvements were relatively modest, and the learning really worked well for only the first few iterations of the LNS. So a lot of work was left to be done, and also the whole idea about decomposition LNS was not as widely used as choosing one set at a time, repairing it, and only then choosing what the next set would be. Okay. So in the standard way of using LNS, you would just choose a single set of variables, destroy it, repair it, and then go back and choose another one. Okay. So in follow-up work on ours, Wu et al. In NeurIPS 2021 used reinforcement learning to basically learn predicting a single set at a time and showed a much better results. So they were able to show that they beat our decomposition-based methods. There are some issues of whether they actually fitted the hyperparameters of our method as well as they did on theirs. But in all cases, I think this is really promising. And it was done on the version of LNS that's more appropriate to most practitioners. Okay, so here though, literally, because we are learning from reinforcement learning, what we're doing is we're just learning from the examples we get and how much improvement we get as we destroy and repair a particular set chosen by the reinforcement learning method. Okay, so, but in terms of finding something that is supervised, directly supervised with offline data, in our early work, we just sampled possible decompositions. But actually, in the MIP literature, the very well-known, expensive, but very good oracle is called local branching. You can think of local branching as the twin of strong branching from branching, but in the LNS sense, something you don't really want to ever do in practice, not on a continuous time while running the algorithm, but something that gives you a really good choices. So what is the idea of local branching, which was proposed by Fischetti and Lodi in 2003? We are going to find the best possible set of variables to change the values of so that we can increase the quality of the solution as much as possible. That means that we essentially are saying that we want to find the reassignment of the variables that satisfies all the constraints of the original problem. We want to still optimize the objective, but we want to make sure that at most k variables are allowed to change values. Right? So here, this is basically saying if xi is 0 in the current incumbent, and now you're going to set it to 1, you're going to pay a penalty. You're going to count it towards the modified set of variables. If the variable is set to 1 and you reset it to 0, you're going to pay in this sum, and this is limited by k. Right? So that means that to find this best set that will give you the best possible objective requires solving MIP that's the same size as the original MIP with an extra constraint. But it can really find good sets. Okay, so based on this, okay, sorry, now I was clicking so much. I got frustrated with the clicker. Okay, so based on this local branching oracle, Sonarat et al. Proposed an imitation-based model for LNS, which basically collected this local branching data and trained a model, right? So much more informed than our decomposition model, where we were sampling randomly these possible settings and hoping we get good examples. So they showed some promising results, but in the paper, the results were a combination between an ML-based initial solution finder plus this neighborhood imitation learning model neighborhood selection. So it was hard to detangle how much of the benefit over skip was given by finding better initial solutions versus the LNS. So, but still, this was, this is a good framework that proposes using local branching for collecting offline data to learn these models. Okay, so these are kind of our baselines that have been before. And so in our work, what we do is we propose to, instead of using imitation learning with local branching, to actually use a contrastive learning for training our model. Okay, so instead of just looking at the best sample, the optimum solution that's returned by solving that expensive local branching MIP during our data collection, what we do is we're going to collect both good and bad samples of possible, proposed destroy sets, and use those during training for a stronger signal to our model. So the idea in contrastive loss is that we want to basically have a function where we have a low value when the predicted action is similar to our positive pair and dissimilar to the negative samples, right? So this usually is proposed in the context of images or graphs, but we're going to use it for our sets, okay? So using contrastive learning in the context of combinatorial optimization is actually a relatively new idea, but we are not the first one to propose it. In fact, there's 2 very nice papers already using contrastive learning in this context, one for decision-focused learning and one in the context of satisfiability. Pashtan was actually involved in the second work. Okay, so how are we going to collect these negative and positive examples? We're going to start solving our local branching MIP. We're going to find the optimum, but while we are finding the optimum, we are finding a bunch of incumbents, right? And it keeps on improving the solutions until it proves optimality. So we're going to use those outputs from our solver to actually record all of the incumbents. And so at the end, we get our optimum solution, but we also get the last k best incumbents before the optimum, right? So all the solutions that are really close to the optimum are also going to be considered positive examples. And we're going to collect negative examples in a slightly different fashion, trying to basically get something that looks like a positive example, but actually is a bad one. Okay? So what we're going to do, we're going to get our optimum sample and look at the improvement that this optimum sample provides over the current incumbent from which we are trying to move, right? So there's a current solution, we're trying to destroy part of it. And so this best improve is how much this solution will move us in terms of improving the solution to the next incumbent. And the positive examples are going to be all solutions that are within half of this improvement provided by the optimum local branching solution, up to a maximum of 10 good samples. Okay? So I hope that makes sense. I'm going a little fast. And for the negative examples, we're going to try to get many more negative examples of in a ratio approximately 1 to 9, where we are going to select 5% of the variables in our optimum set returned by our local branching and change them up, solve this modified set, and see how much the improvement is from just using that set as our neighborhood move. And if that improvement ends up being a very small fraction of the improvement given by the original set, then that's a bad example. So it's an example of a set that's only 5% different from the best possible one, and yet when you actually use it to destroy and then repair, you get a very tiny improvement, right? So that's what we want. We want to make our model be able to distinguish between these very similarly looking sets that actually results in a very different performance. Okay? And if not enough negative samples are achieved by doing this 5% of variables, we then relax this and progressively basically replace more and more of the variables to try to get to these negative examples that will give us the bad improvement. Yeah?
Why don't you use the other suboptimal solutions as negatives?
We could have, instead of increasing the size, maybe try to perturb by 5% some of the other ones.
Or the ones that you didn't select as the positive ones?
The ones that you didn't select as a positive ones.
So if you go back to the previous one. So it seems as if you take the top part as the positive ones, so why don't you just take the bottom part as the negatives?
So they could be very different from the ones that look good. So I think that the idea is that we want to find examples that look like the good ones, but are not good. So we can discriminate, right? Okay. So the features we use are the same features that were used in the Sonerad paper, the Gasse features with the Gasse architecture. We add the Khalil et al. Features that we love from 2017, yay, with Elias during his PhD. I guess I don't know why people are not just always using them, but anyways. And then we have some, so these are static features that are derived from the root LP of the MIP. But then for each particular incumbent we are at, right? So we have the overall MIP, we have a specific solutions we are now, we want to choose a destroy set for that solution, right? So we need some features that actually capture the state, which is the solution itself. These are these features, the dynamic features, which include features from the past W incumbent solutions. In our case, W is 3 solutions, and we look at the value that each variable takes in the last few incumbent solutions, and also what is the value of that variable in the local branching MIP, but solved only the relaxation of the local branching MIP, which actually we have a separate paper you can find on arXiv, where in the process of doing this, we actually discovered some really good heuristic, not ML guided, but heuristics for selecting destroy sets based on relaxing the local branching MIP itself. And so we use that as a feature in our dynamic features, and then the edge and constraint features are the same. So for our ML architecture, we again have we are using the ILP graphs with edges and variables and constraints. We have a graph attention network as opposed to the standard GCN. And basically what we're trying to do is we're trying to predict a value between 0 and 1 for each variable, which will indicate whether we are choosing it to be in the destroy set or not. Okay? So then with that prediction, what we are able to do is we are able to use the supervised contrastive loss that basically looks at for all our positive and negative examples for a particular state, whether our selection, recommended selections of variables here from our model are similar to the positive examples normalized by the similarity with the negative examples. Okay? And so at test time, what we're going to do is we're going to look at the predictions for the variables and choose the variables with the maximum scores to fill in our set of whatever k variables to destroy. So that's also an important thing. We are greedily choosing our set from our predictions as opposed to sampling, which is what some of the other approaches did. Okay, so now I'm running out of time. That's why I'm progressively talking faster and faster. I can talk even faster. But we are using a standard set of benchmarks that has been used in many of the papers on LNS for MIP, where we can easily generate larger and larger instances that are very hard. I'm really hoping to get some real-world instances for this LNS benchmarking. And working with some folks at Georgia Tech to try to do that, like of actual last mile delivery problems that are solved with this LNS with MIP combo. But here we have small instances for these 4 benchmarks on which we're going to train and test. And then to evaluate generalization, we're also going to test on double the size instances, right, without training on them. Okay, and our benchmarks are going to be running branch and bound alone, doing LNS with a random selection, doing LNS selection with this novel heuristic based on the relaxation of the local branching MIP, using the imitation learning LNS for Sonarat et al., and using the reinforcement learning based LNS from Wu et al., right? So the newest benchmarks versus ours, which is going to be annotated as contrastive learning LNS. Okay, so here are the results. So our method is in this bright purple, branch and bound is in gray, and then our strongest, competitors are the RL in blue and the imitation learning IL LNS in pink. And so for vertex cover, for both small and large, we can see that we have a dramatic advantage over the other methods, with imitation learning being the second best. For maximum independence set, we're still the best, but the difference in performance is not as dramatic. For combinatorial auction, we have also big improvements for both small and large instances. And for minimum set cover, again, contrastive learning is the clear winner with here the reinforcement learning is maybe the second best algorithm, right? Interestingly, in some of the benchmarks, this our new non-ML guided LB relax heuristic actually also is doing really, really well. But overall, the contrastive learning-based model is really outperforming in all of our setting by a significant margin. So here you can see basically the kind of same results by divided by primal gap and primal interval. So here we are reporting the primal gap at 60 minutes. So it's kind of a point estimate of how much were we able to close within that 1 hour. And so you can see that, again, that contrastive learning methods is performing the best. With maybe the imitation learning being the second best in terms of these results. But what we really want to do, we want to actually be focusing on the anytime performance. How quickly are we closing that primal gap over time as we are solving? Because maybe we need to stop the search at 30 minutes or 10 minutes, etc. And so that's what the primal integral gives us. Integrates over all of the runtimes up to 60 minutes. And according to that metric as well, the contrastive learning is outperforming all our methods. And again, imitation learning LNS is second best. Okay? So these were all results on the small instances. The story on the large instances is very similar, except that here, branch and bound is really having a hard time. Right, so it kind of skews our axis here. Okay, and in terms of the integral, similarly again, contrastive learning is doing great on the large instances, and here in terms of the other approaches, it's a mixed bag between reinforcement learning versus imitation learning being second best. So one last, so I'm gonna skip this, but this is like other results. So we did an ablation study to study the effect of our choice of doing the edit features of Khalil et al., which we call full features, versus the partial features, which are the ones used by other papers, and replacing the GCN architecture with the GATT architecture. Essentially what we find is that even if we give the GATT architecture and the extra features to the imitation learning LNS, is still worse than any of the contrastive learning versions, even without changing, like using partial features and using the old architecture, and definitely significantly worse than our architecture that we've actually deployed for the experiments. So both of these changes, both the added features and the modified architectures, are actually helping us improve not only our approaches, but potentially other approaches as well. Okay, so in conclusion, lots of exciting stuff in both directions, integrating machine learning into combinatorial solvers, integrating combinatorial reasoning into machine learning pipelines. And if you want to learn more about what's going on, visit the posters of Tawan and Aaron tonight. Thank you so much.